Hi, so the last talk we had a two-dimensional plane region that we were trying to find the area in between. And the method we used was to divide from A to B up into n sections, and we took a section that was the kth section from xk minus 1 to xk, and we picked somewhere in there, and it could be any place, we picked the c sub k, a value of x, to get the height of a rectangle, because we know how to find the area of a rectangle. So we use the width of the rectangle to be x sub k minus 1, which we've always called delta x sub k, and then we add this rectangle. And we just added up n of those rectangles. There was a little bit of error in here, so we took an infinite number of really skinny rectangles, and then there was no error. They just became straight lines, and we were kind of shading in the region, and we got a perfect area. Well, the only difference today is we're going to take that same region and rotate it around this axis. This is called the axis of revolution. And what we're going to form is a three-dimensional figure, and we're going to try to find the volume of that three-dimensional figure, which is called a solid of revolution. Just shortcut SOR. So there's no sense in reinventing the wheel at this point. This method seemed to work really well, so we're still going to divide it up the same way. We're still going to make that rectangle, but now we're going to take that rectangle and rotate it around this axis. We're no longer going to have a rectangle. What we're going to have is something that looks like that. And this would be delta x sub k, and this right here is the radius, would be from here to here. So what kind of figure is this? Well, if you turn your head to the side a little bit, it looks like a right circular cylinder, something that we do know the volume of from geometry. The volume of a right circular cylinder is pi r squared h. And in this case, the h is going to be my delta x sub k. And then I need the radius. Well, the radius is this height right here. And it's going to depend on where you are along the x-axis. It's a function of the x value, and in this case it's c sub k. It's not f of c sub k unless this axis was the x-axis, because f of c sub k would be this distance and we only want this. So it is a function of that value of x, and it is going to be a radius, so let's just call that little distance r of c sub k. And then we can put that right in here. And that's the volume of this one right circular cylinder. By the way, it's given a name. It looks a little bit like a hockey puck, but it's called a disc. And I think you could buy that. It looks like a little disc. But we have n of these. So what we have to do is add them up from k equals 1 to n. But again, because of that little bit of area in there, you're going to have an error. So to avoid that error, like before, we're going to take the limit as n approaches infinity, or as the norm of the partition approach 0. And then these disks are going to be so thin that there's going to be no air, and this is perfectly going to give us the volume that we're looking for of this solid of revolution. And the nice thing we noticed, again, we have an infinite Riemann sum. Except instead of f of c sub k, we have this function of c sub k. But it's still going to be a definite integral. It's going to be the integral from a to b of pi r of x squared dx. So we've got a definite integral that's going to give us what we're looking for, and that's really good news. Now, normally, if you see the formula, they take the pi out front. But otherwise, that is the formula for disks. So we can just box that off and put a little star next to it, because that's going to be pretty important. Now that we've got that, let's try an example. Find the volume of the solid of revolution when the region bounded by this function and the x-axis only from 0 to pi over 2 is revolved about the x-axis. So this time we are going to revolve it about the x-axis. Well, the first thing you need to find is a little bit of a sketch. Well, the sine of 0 is 0, and the cosine of pi over 2 is 0. And everywhere in between that, the cosine and the sine are positive. You're going to get something that looks like this. You don't have to have it exact, but since 2 sine of x cosine of x is the sine of 2x, we know that this is going to look a little bit like a sine function. Anyway, the first thing you want to do is make your rectangle. Just like when we were finding areas, and that would be dx. And then you can write down the formula. Volume equals pi integral. And instead of writing r of x, I always just put that and know that you're going to have to find the radius. And we know we're going from 0 to pi over 2. So if you know the formula, the only thing we really need to know is what the radius is. And the radius is the distance from the x-axis up to here. Well, in the xy coordinate system, the distance from the x-axis up is always called y. Or, in this case, the square root of cosine of x sine of x. So if we can solve that definite integral, we've got our answer. The nice thing, even though this looks a little complicated, when you square that, you just get cosine of x sine of x dx, which isn't a formula that we just know, but a few talks ago we learned about u substitutions. So if I let u, you could either let it be the sine of x or the cosine of x. I'm going to pick u to be the sine of x. Du is cosine of x dx. So then this writes nicely as just the sine of x is u and the cosine of x dx is du. But those are x values, 0 and pi over 2. We have to turn them into u values. So the sine of 0 is 0 and the sine of pi over 2 is 1. So now we've completely rewritten it into something that is a form we know how to do. This is u to the nth du, where n is equal to 1. So the antiderivative is u squared over 2. We're going from 0 to 1, we just get 1/2 minus 0, pi over 2. So we've done our first volume of a solid of revolution. It would be this many cubic units. And a cubic unit is just, if you took 1 on each side, that would be 1 cubic unit. And we got practice on our U substitutions, which is always a good thing. Okay, let's try a second one. Find a volume of the solid of revolution when this parabola 2 minus x squared and y equals 1, this horizontal line, form this region. And we're going to revolve it this time not around the x-axis, but around y equals 1. So we've got our region, we've got to put in our rectangle, and realize we only have one way to make the rectangle, because to really make a disk, the rectangle has to be perpendicular to the axis. So I had to make my rectangle that way. So this is dx, and then I can just write my formula. Pi integral radius squared dx. So we still need to get the limits. We have to go from this x value to this x value, so we do have to find out where the parabola intersects this horizontal line. So we set 2 minus x squared equal to 1. We get x equals plus or minus 1. So nicely it goes from negative 1 to positive 1. And what goes for the radius? Remember, we measure in this direction from the x-axis. So from here to here is the y value on the parabola. So that's 2 minus x squared. And then this area right here is 1. So we have to subtract 1. And we've got our setup. Now, to make our life a little bit easier, what we could say is, this is a parabola and it's symmetrical around the y-axis. So we could just go from 0 to 1 and double our answer. And then before we square this out, we want to make this 1 minus x squared. So now we're ready. We square this out and get 1 minus 2x squared plus x to the 4th. We don't need a U substitution. We know how to take all those antiderivatives. The antiderivative of 1 is x minus 2x cubed over 3, and then plus x to the 5 over 5. Then you just plug in, you get 1 minus 2/3 plus 1/5. And when you put in 0, you get 0. So 1/3 plus 1/5 is 8/15 times 2 pi is 16 pi over 15. And we've got the volume. Now, I'm not going to go through this in great detail, but we did this when we were doing areas. There's no reason, if I wanted to revolve this around this axis, that I couldn't make my rectangles on the side. And then I would just divide from here to here, say from C to D, I would divide it up and I'd call them delta y sub k for my widths. And the only difference, this would be r of c sub k, but it would be in terms of the variable y. So the only difference is, this would be pi times the integral from c to d of r of y squared dy. And we'll do some examples of those when in the next talk we do. Now, one thing I'd like you to know is we're not doing these volumes of revolution just because they're fun, even though they are. In the real world, these solids of revolution are something that are made in manufacturing quite often. One reason is they look really nice and they're very practical. For instance, what if we had a function that looks like this? If I were to take that and revolve it around the x-axis, my artwork isn't so good, but if I were to revolve that around, it would make like a water bottle. So a lot of things that are manufactured are solids of revolution, and so we really would like to be able to find out what is the volume inside of one of those solids of revolution. Okay, since we have a little bit of space, I just had an idea here. What if we were to take a straight line function and say we went from 0 to h, and in this direction we went to r. And we got this right triangle, and we revolved it around the x-axis. I wonder what kind of volume we would get. So what we could do is just make a rectangle perpendicular to our axis. So then we could write out our formula, pi integral from 0 to h, the radius squared dx. Now the radius is the y value on this function, but I didn't give you the function, so we can get it though because it's a straight line that goes through the origin. And what's the slope? The rise over the run is r over h. So y equals r over h x. That's the equation of that line. So I can just put that. Now r and h are just constants. So I could take the r squared over h squared out front along with the pi, and then I just have x cubed, or x squared dx. And the antiderivative of x squared is x cubed over 3. So when I put h in for x and 0 in for x and subtract them, I just get h cubed over 3. And I have to multiply that by pi r squared over h squared. And nicely, h squareds cancel out, and I'm left with 1/3 pi r squared h. So what have we found? We found the volume of this solid of revolution, which I think you can see would be a cone. So not only can we use these volumes of revolution for manufacturing, but we can also use them to find some formulas that we used in geometry. So good. Thank you.